So we're going to look at, in relation to foundations, we're going to look at drain tile, like how it works, what it's doing for us, why we do it certain ways. We're going to look at backfill, so both how different materials function as backfill, and on how different materials cause different loading on our foundation walls, and then waterproofing. So with our drain tile, we have a couple of different options on what we can do with that. You guys have all seen like the corrugated black pipe, right? So that's probably the most common option, and that's a really nice product. You get this corrugated black pipe, and it just has like little cuts in it all over on all sides, and then it has a like polypropylene sock on it that is supposed to keep fine particles from getting into the pipe and plugging the pipe. And so the other option is, well, there's a couple there. The other common one is 4-inch PVC, perforated 4-inch PVC, like sewer pipe, stuff that they would use to build like a drain field. Usually those will have holes drilled, like they'll have two or three rows of holes drilled. So like they'll have holes on like half of it or a third of it or sometimes 2/3 of it, depending on the manufacturer. And so a lot of times with that, when we run that stuff, we'll put like the holes on the side or something and leave like solid pipe on the bottom, so that as the water runs in, it just is unobstructed and can like run right to the sump pit or out to daylight. And another system for drain tile, there's a product, I believe CertainTeed makes it. It's called Formadrain, and it's like a 2-inch by 8-inch plastic form, and it has slots cut in it. So it's a hollow plastic extrusion that has like 1 or 2 dividers in the middle to stiffen it, and then slots cut in it, and you use that to form your footings, and then you don't have to strip the footings because that's your drain tile. You just dump your rock in, put your fabric over it, done. So I can probably, let's see, I'll see if I can find a picture of that stuff for you guys quick. Let's see. So here we go. There's the Formadrain stuff. So you can see here they have, you know, where this line is. That's where that inner rib in it is to stiffen it. And but super nice system. You know, you can see in the background here they've got it set on their stakes. They have these corner pieces, and so, oh, look at that. They got these nice little spreader bars. That's kind of a nifty little thing. And you can set your rebar right on that. Nice. So, anyway, so that's a really nice product. We have definitely have used that on projects in the past, and so depending on the project, it can be a really nice way to go. So, and so basically, all the drain tile systems, they're just creating a air pocket down there for the water to flow into, and then it creates that open space so it can quickly run to the drain, you know, whether that's out to daylight or into the sump pump basin. And the other thing it does is it creates ventilation space if we ever need that for radon mitigation. So we don't have a ton of soils around here that have radon problems, but radon is basically a radioactive gas that comes out of some types of soil, depending on what the rock formation is. Like typically you see it in more like rocky type soils, you know, that are like on granite or like, so like an area like Melon would have a higher probability of having radon than like Mason.
I'm sure he probably has a lot of it.
Maybe, you know, and it's there's different theories on it, but basically you have to have radioactive material in the soil,
Yeah.
and as it decomposes, it lets off this radon gas, which is, you know, contains some of the radioactive particles in it, and it like flows through cracks in or fissures in the soil and can come into your foundation. So with our drain tile, we can put a fan connected to that tile. And so just like our sump pump creates a place for the water to drain into, and then we pump it out, when we tie a pipe into our drain tile and then run that pipe out and put a fan on it, so we have a fan pulling on that drain tile, then any of that radioactive gas that goes into the tile gets sucked out by the fan and blown outside where it won't bother us. So,
When you're putting in drain tile, is there like a minimum like slope you have to put it at?
we usually run it level. So, you know, if you wanted to, you could like be like, oh, we're gonna make this the high side and run it to our sump pit. It's really hard to get to create a uniform slope, where if we did a good job with our excavating, the trench should be pretty level to the bottom of our footing, and so we just run it at that. Like, we don't really care if there's some water by our footing, we just don't want it to get higher than the footing. Because this is maybe one of the more important things to remember, because we've seen this get done incorrectly a lot of times. So this here is our undisturbed mineral soil, you know, or if we overdog or hit bad stuff, our compacted granular fill, our footing on top of it, and then our wall is coming off of our footing. So we like to say that our tile needs to go to the bottom of the footing depth. So it would go like this. The reason for that is, in most cases, we're going to fill the inside of the foundation to the top of the footing, and then we're going to pour our floor here. We do this so that it resists any lateral force from the soil. It makes the wall bump into the floor, so it is extremely difficult or impossible to push that wall sideways. The other thing is, then, if this footing is 8 inches, which that's the shortest footing we can build in Wisconsin, and then this floor is 4 inches, we would have to get 12 inches of water to have any water be able to come out on the floor. And so that means, like, probably the highest amount of water we would ever be able to get in the soil would come to like the middle of the drain tile, which still gives us 10 inches of buffer to the top of our floor. So if it's level, we don't really care if there's a little water in there. We just don't want the water to start filling up in the soil. So, okay. Okay, So our sump basin, you know, it basically makes a low point. The water can all run out of the tile into that. And then we put our pump in there. Usually we'll have a submersible pump. You'll see in a lot of older homes, they have pumps where the motor is up here and then it's got a shaft that goes down to the pump. And those are totally fine too. They seem to have more problems than the submersibles. So, and they have to be like held, braced in place, or have a really good pipe system if the pipe is screwed into that pump section at the bottom well, and then they can work fine. I've just seen a lot of them that are in really, really bad repair. So we're always putting in submersible pumps. So the sump basin can be solid, like can be completely sealed, or it can be perforated. It doesn't really matter. The one caveat to that is if we're doing work, so we do a lot of this type of stuff in a crawl space where we don't have access to the outside, so there's no tile outside. So we're running this tile inside to catch any of that water that pushes in under the footing or like runs through the wall. And then we're running that tile and we're putting in these pits that have a plate on the bottom that sticks out past the edge of the sump basin, and then they're perforated. The reason that they're perforated is not to let the water out of the basin into the soil, but to let the water from the soil into the basin so that it doesn't act like a boat and get saturated soil and pop the pit right out of the ground. So the perforation relieves any hydrostatic pressure. It just lets the water bleed into the pit, and then it won't push it out of the ground. And that's why we're running fabric like this, and then filling this space with washed rock so that it creates a filter and a clean space so that we don't have fines plug the holes in that pit. So, because if these holes plug in it, that thing's gonna float. So, the same, just like a rabbit trail, I guess. Same thing with sometimes brand new septic tanks. If they don't have enough fill over them and you have really wet soil, plumbers just put it in, and then you get a big rain that nobody was expecting, it'll float those concrete tanks right out of the ground.
Wow.
That's
So,
crazy.
okay, and then the one important thing on these sump basins is like, we don't want to put a 5-gallon bucket in there because the diameter of the bucket is so small. If we're getting a lot of flow in, what happens is, you know, you put a pump that's pumping, I don't know, some of these like 3rd and half horsepower pumps probably pump 20-something gallons a minute. And so you put it in a 5-gallon bucket, the switch turns it on, bang, you know, it pumps the 1.5 gallons out in whatever it is, 15 seconds. And then the float drops and it shuts off, and there's water running in, and so it's like turning on and off multiple times a minute. Where when you put a larger capacity basin in, something that's a larger diameter at the bottom, even if it's, you know, filling up 8 inches and then the float turns on and it brings it down to 1 inch in the bottom, you're still running like 6 or 7 gallons of water. And so that pump turns on, runs for like a half of a minute, shuts off, and then the water running in, you know, takes a couple of minutes, and you don't end up having that short cycling of that pump burn it out. So, because like with electric motor startup, single phase electric motor startup, they are typically capacitor starts, and that's when they generate the most heat, is on startup. And so if they're having to start like 3 times a minute, it can really overheat them fast. So, and that will cause really short lifespan work pumps. So we want to have, like, if you have an option to put a bigger sump basin in, always go to the bigger basin. Not necessarily depth. The depth doesn't necessarily matter. It's more diameter. So with some of the old separated sump pumps, where you had the motor, then the long shaft, and the pump at the bottom of the shaft, those had like a float rod, and so those guys you could set where the float is. And so for those, the deeper basins worked great, and the diameter didn't really matter so much, because you could raise the float, 18 inches off the bottom of your pit, where it won't turn on until it hits that. And anyway, so those guys, that's the one benefit of those pumps, is you can set the float. There are some that I've seen at the hardware store too, where you have a shaft where you can set the float, so you have a longer run time. So
That's for the ones that the pump isn't in the sump basin? Or?
Yeah. Because so a lot of the submersibles will just have this little float with an electric cord, and it's like, as it drops down, then whatever their switch inside of that is turns off, and then as it floats and it turns it upright, then it turns it on. So there's like a little gravity thing in there that turns it on or off. The other type will have an arm that sticks out of the top of the pump and a shaft that goes down, and the float will just slide on the shaft until it hits the top of the arm. That trips the switch, turns the pump on, and then as the water goes down, the float slides back down the shaft until it hits the bottom, and the water goes down, chink, and turns the switch off.
Just like a toilet.
Similar, yeah. Yep. So,
On top of the wash rock of your sump pump, you pour concrete.
in what spot, like?
Like, right on top, like right here.
Oh, like in a crawl space?
Yeah.
So if we were doing this in a crawl space, we would just run our liner,
Yeah.
like the edge of the pump or the edge of the basin has a ledge, so that you can put a lid in here and then screw it down. And so if we're doing a crawl space, we would do this, and then we'd run our plastic over in the ledge, and so then as it screws down, it seals the moisture under here. It keeps all that water vapor out. If we're doing it in the basement, then we set our basin, and on these we can have a non-perforated pit, and we don't have to do this filter fabric and rock if we have a non-perforated one, because then, our soil grade is here, and then our concrete gets poured, and the concrete locks that sucker in to where it's not ever going to push out of the ground. So
What if you chisel away the concrete and then put a sump pump in?
you can do that. So, in that case, like, let's say, here's the corner of your basement, and you want to put a pit in here, like, you just jackhammer this out, dig your hole down to where you want to, put your pit in here, run your drain tile into it, and then we mix up some sack cream or something and pour to fill that back in. So.
Okay.
So, and in this case, like, I have done this type of a thing, except in a basement where there was no drain tile, and then we did this, dug this down 2 or 3 feet, put filter fabric in, you know, a little bit of gravel, set the pump or the pit where we wanted, filled the rest with washed rock, and then poured this concrete back in for the floor. So there was no drain tile, but the guy had water under the foundation, and that was just enough to relieve. Because it's like when we take a break, I'll look up. There's some really interesting videos that guys have done on like hydraulic flow through soil, about like how it can cause dams to fail. And so they illustrate really well how water flows through the soil. The same things that they want to prevent on a dam, we can create with a sump pit to cause the elevation of the water in the soil to change. And so, first break, I'll find a video on that, because it can help understand like why if we put a pit like this in, why even with no drain tile running to it, it'll help dry out a basement. Okay, why would we ventilate a drain tile system? Any thoughts?
For that radioactive stuff and to keep, I don't know.
Well, the answers are right there. If you can read, you know the answer's right. So number one most important thing would be if there's radon in the soil. So anytime that we build a new home, we always want to have drain tile to code, like with a drain tile inside and outside of the foundation, and we want to run it to so there's two schools of thought on that. If you guys have worked and put in any of those sealed sump pits that we've put in, they always have a 3-inch hole in the lid, right? And a lot of times we just have a little chunk of PVC with a cap on it, plugging that thing up. So that's because we're in a place where it's like, we don't really think that we need the ventilation, but if we do, we can just run a 3-inch PVC, we pull that capped piece out, drop a new one in there, run out through the rim joist and put a fan on it, or out through the attic and put a fan on it, and then it can, because that pit is sealed, that fan pulling on it will pull air. So, you know, let's say here's our house, and we've got, we'll draw it in red. We've got our outside drain tile, and our inside tile. And then we got leaders every 6 feet. For air, we technically would really only need one because of the way air flows. And then we have our sump pit right there. So we run our 3-inch tile, 3-inch vent here, and it goes out of the house, and we put a fan on it so that it's sucking on us all the time. So the first thing that can happen is this inside drain tile. This drawing is a little bit messed up now, but you know, we've got our concrete floor and our tile, and now if we put a negative pressure under here, and negative pressure there, and we're positive there, we can actually get air come down and flow from our basement into that tile and then exhaust it out. So if we do that, typically this air is going to be more dry than the soil or this here, and so as you have dry air flowing down into here, it'll help keep the floor dry. The other thing that it does is this will cause, you know, like a negative pressure further away from the pipe, the less negative it gets, but you'll create this zone of negative pressure. You know, in this case, probably within our filter fabric, all within our rock. And so, if there's any air connection at all to any of these spaces, we will pull air through that soil, and over time, the airflow through that soil will dry it out like really dry. And so, it's actually quite incredible how much water air can get rid of. So when you're moving air, it can transport a massive amount of water.
That could be an option if you have a wet basement and you already have drain tile and you just
Yep.
put ventilation in there.
Yeah, so if, in that case, like let's say you have drain tile, so the one challenge would be if you have drain tile that's going to daylight. You'd want to put something in so that if it sucks on it, that it'll close a backdraft damper or something, because we have winter time and we don't want to be sucking minus 30 air into there.
Right.
It's not a huge amount, so like maybe it wouldn't be the end of the world, because at minus 30 air is going to be very, very dry. And so, you know, if it's 85, 90 feet out to the end of your daylight drain, by the time you pull through, you know, 80 or 100 feet of soil, that air is already warming up, and then you get in around the house and it's warming up more. And as very dry air warms up, its capacity to hold water goes up, and so it can pick up a huge amount of water. So probably wouldn't be the end of the world even if you had a drain to daylight. But what you can do is you can take, if you know approximately where the drain tile is, you can get a concrete core drill right into that tile, or even like in close proximity to it, even if you were a little bit off and you drilled here, then you just make sure that you got material that air can flow through. You stick your PVC pipe in there, run a bead of caulk, run it up to your fan, stick your fan on, and turn it on, and it'll start pulling through there. So, I was in a class quite a few years ago, and the guy teaching the class was from like Kaukauna, Green Bay, whatever. He said they have a lot of radon issues there. So he said almost every house has they at least have a system that they can put a radon fan on. Because you don't necessarily, if you're building on a new site, you don't know if it's going to have a radon issue. So we want to build it so that we can mitigate the radon. And then after it gets closed in, then you just do a test and see is there radon here or not. But so you need to have it capable of dealing with the radon before you know the radon's a problem. So this guy gets called by a builder and he's like, man, we built this house a year ago and the customer uses the basement to do their like exercise stuff. And he said they set their rubber exercise mat thing down, and he said within a couple of hours there's water between the concrete slab and the exercise mat. And he's like, I can't figure out why. And so the guy goes out there and he's like, man, it's gotta be really wet. And he's like, what did you do? How did the slab go? You know, and he's like, well, it was like 6 inches of washed rock and then plastic and then the concrete. And so finally they decided that they were gonna core drill like this to put in a active ventilation system. And he said they drilled the hole, and he said the concrete guys had poured the floor on a Friday, and they wanted the bleed water to come out of the concrete quick so that they wouldn't be there late on a Friday night finishing it. So instead of putting the plastic on top of the washed rock, they put it down over the mineral soil, put their 6 inches of washed rock on top, and then poured the floor. And he said that 6 inches of washed rock was completely filled with water. So he said they stuck their pipe in, ran their bead of caulking, went out through the rim joist or through the attic, and put a fan on it. And they're like, we'll just let that fan run. And they came back in like a month, pulled the pipe out to check it, and he said all the water was gone. So
How big of a pipe do you put in there? 4 inch?
I would go 4, yeah.
And you need a tap right into the drain tile, don't you?
Not necessarily. In that case, they just stuck it into the washed rock in that house. So,
Well, did they put plastic on top of the wash rock and then the cement?
no, they had it under the washed rock in that case.
So, wouldn't the
So then-
concrete seep into the wash rock?
No, the water did. So, and then if you get any holes in the plastic or you have a seam in it, the groundwater comes in, and then the weight of the groundwater pushing on the plastic seals it somewhat, and then the water can't get out. It acts like a pool liner.
If you have a 4 inch PVC pipe running to a 4 inch drain tile for your ventilation, it would cause a lot more even pressure around the whole place.
It would. So, but even like, you would be surprised how porous like anything that would work as like an engineered fill or a granular fill for us. Like any material that we can fill this area with that will meet our like engineering specification on it, air will flow readily through those materials. You know, whether it's clean sand or washed sand or P-rock or 3/4 inch washed rock, air will flow through those things without hardly any resistance. So, especially the volume that we're talking like through a 4 inch pipe. You know, we don't need that much air. And those radon fans create a huge amount of suction pressure, and so it'll pull through that material really easily. So we ventilate our drain tile if we've got radon and if we have to deal with really big wet soil problems. Okay, so one of the big things that we need to go over to understand a lot of the foundation stuff is we have to understand what direction water vapor moves. So you guys have any ideas, like what causes water vapor to move?
Changing air temperatures.
Okay,
Air pressure.
okay.
Dew point.
Maybe. So when we looked at heat flow in one of the earlier lessons, what do we look at? Like how does heat flow
Hot to cold.
from hot to cold? Yeah. Okay. So it can use radiation, convection, and conduction, but it's gonna move from where it's hot to where it's cold. So with water vapor tends to go from warm to cold, it always goes from more to less. And that typically is from hot to cold. Okay? That's why, you know what you said, Neil, you have condensation. The reason that you get condensation is because the water vapor flows to that cold surface. And so, in our houses in the wintertime, our vapor diffusion moving from hot to cold, what direction is that going through our walls and roof and other surfaces of our house?
From inside out.
Okay. When we have a basement that's like 50 degrees in the summertime and it's 80 degrees outside and 80% humidity outside, where does the water vapor want to go?
Basement.
Into the basement.
Yeah.
Okay? So, the other thing I want to go over with you guys that we will get into more in depth later, but I want to introduce the concept here. One of the methods of heat transfer, convection, what is the biggest driver of convection?
Wood.
What's that?
Wood.
Wood?
Yeah.
Not exactly, not the answer I'm looking for.
What?
What drives convection? Like the mixing of
Moving
air.
Air movement.
Yeah, what is like, if we aren't doing it
Temperature change.
mechanically, if we aren't forcing it to move, what makes air move?
Temperature change.
Okay? Okay? Why does temperature change make air move?
Because heat rises and cold sinks.
Nope.
Hot air rises
Hot air rises. Why?
because the molecules are more active and so they try to get away from each other.
Yeah, it gets bigger, right?
Mm-hmm.
It weighs less. That's why a hot air balloon works. You blow a big fire into that balloon and it rises. Why? Because the air is less dense than the air around it, meaning it weighs less and it can offset the weight of that basket enough that it can pick the basket up and you can go flying across the world with it. So that exact same thing works in our houses. How many times have you guys been in a basement that's hotter than the upstairs in the house?
Never.
Almost never, okay?
Unless you have a fire going or something.
Okay, yep. So, in our typical house, we're going to draw this one really tall. So, this one happens to be below grade. It's got a basement there, first floor, and we got a story and a half space. So, we have our nice forced air furnace here in the basement. The air down here is 58 degrees. Here we're 70, and here we're 74. Okay? What area of the house is going to have the highest pressure?
The basement.
Nope.
The top floor.
Top floor. Okay? So this is going to be like big positive up there, right? Because as we're heating this air, it's rising and it's trying to make this house float, right? It's trying to lift it right out of the ground, except our houses are way heavier than a hot air balloon basket. So it can't quite do it.
That would be something
Okay.
if you had a
So
big
what does that mean then about down here? In relation to this part of the house, will this be a positive or negative pressure?
Negative.
Negative, okay? So, will this be positive or negative related to the outdoor?
Negative.
Negative. So, we're going to say we have positive out here, negative in here. So, what does that mean when we have a hole in our basement? Is air going to flow in through that hole or out through that hole? It's going to come in, okay? So we got this air coming in. So the interesting thing is this dynamic doesn't really change that much summer to winter. Actually, sometimes in the summer it can be worse because we have the sun, you know, happy, smiling sun shining down on our roof. And so instead of being 74 here, this might be 82. And this here is probably 65. So this basement is still going to be massively negative compared to the upper part of the house. Incidentally, like because we're negative here, these holes, the air is leaking in here. When we are up here, we have a hole here. Is the air going to be going in or out?
Out.
Out. Okay.
Would the water vapor travel from the top of the house down to the bottom as well?
Not necessarily.
What if there was still oxygen? I mean, what if there's still?
There's
What if there's? What if there was still? What if the upper room was still a lot cooler than outside? Would the air still go through? No.
Yeah. Because the pressure inside will overcome, and wants to flow from warm to cold anyway. So we both, up here, we have both the temperature wanting to push out and we have the air pressure wanting to push out. Here, we have, let's say it's 10 degrees out here. So the heat wants to flow out. Our heat drive, the push of our heat is from more to less. So our heat is still going out. Where's the red marker go? That's right there. So our heat is still flowing this way, conducting. Okay. But because we have a negative air pressure compared to the positive out here, we have cold air flowing in. Okay? And so that's where it's important to be able to differentiate air pressure, you know, or convective movement of heat and conduction. Insulation in our walls, what kind of heat flow does that resist?
Conduction.
Conduction. It only slows down conduction. It has no bearing on convective heat loss, and it has no bearing on radiation. Okay? So it's only one form of heat flow that it's helping with. So the reason I want to talk about this is because, like, we're talking about foundations today. We talked, I think, last week about why we insulate, you know, and so this conductive thing, heat flows from warm to cold. And so if this soil is 45 degrees, we have heat flow through the basement floor. But what I wanted to talk about this is particularly in the summertime. So we're looking at the 65-degree basement, and we have 80-degree outdoor air. Like, that's relatively common for us, right? It's not like 102 that we get like one day every 3 years or something, but we get 80 a lot. And so when we have this air leak, or in the case of our really nice vented crawl space, we have these big gaping holes that people put in there, you know, or some people that don't understand, they're like, yeah, I want to dry my basement out, so I opened up the basement windows to ventilate it. And so I want to look at what's going on with that. Okay, so I have, we'll look at this one a little bit. I have in front of you guys this psychrometric chart, okay? So this is a really, really fascinating thing that you could spend a lot of time. It's kind of like a wormhole thing. You like go down it and it never ends. But it can really help us to understand the dynamics of air temperature and moisture. So what did we talk about earlier? Why does hot air rise?
Because it expands.
Because it expands, it gets bigger, the molecule grows, right? So when the molecule grows, let's theoretically say that this balloon is one molecule of air. If I bring that down into this basement and it cools down to 65, is it going to expand or shrink? Okay? So it's going to be this size down here, and if I put it up here, is it going to be bigger?
Bigger.
Yeah. So it's going to be this size up here. So if right here it is 85% full of water. Let's see if I have a blue one. Okay, so it's 85% full of water. If I put it down here, what's going to happen?
It's gonna be 100%.
It's going to be more, like it'll be 100% and we'll have this much left over. And if I move it up here, it's going to be like half full, right? So this chart, this really, really cool chart, shows you exactly what's going to happen. So if you look at these curving lines, so if you look right down here, it says 8% relative humidity. Okay, so the curved lines, the like hockey stick lines, that's your relative humidity. So if we're looking at this air here, somebody find me the 85% relative humidity line.
All the way right here, right? 85?
So we've got a 90% and an 80%. So it'd be this curve in between those. So you're looking at the curved line. Okay? So there's 90, there's 80. So it'd be right halfway between those. Okay? Then, if we go to the bottom and you see where it says dry bulb temperature degrees Fahrenheit, in the very bottom of the chart, everybody see that?
Is it this part right here?
Well, yeah, it's
Dry bulb temperature, so all these temperatures here, okay? So then find the 80 degrees and follow that up until it intersects with our 85% RH curve. All right? So then, if you just take your pen and put a dot right at that intersection. Okay? Then, let's see, I'm going to do it here. Okay, so 80 degrees and 85% RH. If you follow that out to the left until it hits the very edge of the curve, okay? So our dot here for where our air is at, we go straight to the left to this outer curve. What temperature is that at?
75?
75. Yep.
Oh, you're looking over here.
So you go all the way to the bottom and follow that line straight down until it hits your temperature at the bottom. Okay? Okay, you see that? So we went to there. Also, we're at 80 degrees and 85% RH. And then we bring that across to here. and you go straight down, and what temperature are you at?
75 degrees.
75. So if you've got 80 degree air that's at 85% humidity, the dew point, or the 100% relative humidity temperature for that air is 75 degrees Fahrenheit. Okay? So if this air cools 5 degrees, you're going to get condensation.
See ya.
Okay? So what happens then when we run this air into our 65 degree basement? We get condensation on everything, right?
And then it all flows upstairs.
Every surface that's below 75 degrees is going to be wet. Okay? If we don't have insulation under this floor, what temperature do you think this floor is going to be?
45.
Like 45, you're very close to 45. Some, maybe a few degrees over because there is some heat flow.
It's gonna dump
So,
water on it.
so that floor is going to be swimming. What's going to happen to these walls, at least the below grade part?
They can be wet.
They're going to be wet, probably at least, a third, you'll have some heat flowing into this concrete from the outside and in the summertime, but, 2 feet below grade and down, it's going to be wet. So the same thing happens in our crawl spaces. Like people put a vented crawl space and they don't have plastic, a vapor barrier over the soil. So you get water coming out of the soil, you get highly humid air coming in through the vent space, and everything in that thing is going to be wet. A few years ago, I went to a crawl space out on Lake Namakaw, and they wanted insulated. It was like 50 feet from the lake, and the floor of the house was 3 feet above the water level of the lake, and they had a crawl space under it. I went in there, every single thing in the crawl space was dripping. Every beam, every floor joist, the wall, everything was dripping water. The floor system. And it was so rotten, like all the structural beams were rotten, most of the floor joists were rotted halfway up. It was a complete disaster. So it's really, really important for us to, we're going to go over this a little bit more so that you guys can get to, at least have a cursory understanding of this before we move on. Because it can really, really help us to understand if we go into a basement on one of those days and it's wet and a customer thinks, my basement's leaky, it just rained last night and everything's wet. Maybe, maybe not. Maybe they have an air leak somewhere and the 95% humidity air that's coming in because it rained yesterday is just condensing on the cold walls. That's when you want to know some more information. Are the walls insulated? Is the floor insulated? What's the temperature? So, okay, let's take a little break, and you guys can go to the bathroom or get more coffee or whatever. This one pulled up here, Stuart, to this guy does a really nice job of illustrating this particular thing about, the title, the bizarre paths of groundwater around structures. And so our drain tile systems, or even a perforated sump basin, can dramatically alter the groundwater path around the structure. So, how long is this one?
14.
Okay, so we may not watch the whole thing, but we'll see. This guy does some really good stuff.
An unusual incident happened on the construction site for a sewage lift station in British Columbia, Canada. WorkSafe BC, the provincial health and safety agency, posted a summary of the event on YouTube. A steel caisson had been installed to hold back soil while the lift station could be constructed. One worker on the site was suddenly pulled into a sinkhole when the bottom of the caisson blew out. The cause of the incident was related to groundwater within the soils below the site. We don't all have to live in fear of the ground opening up below our feet, but engineers who design subsurface structures do have to consider the impact that groundwater can have. The solutions to subsurface problems are almost always hidden from public view, so you might never even know they're there. This video is intended to shed some light on those invisible solutions, including what could have been done to prevent that incident in BC. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about how groundwater affects structures. Groundwater has always been a little mysterious to humanity since it can't easily be observed. It also behaves much differently than surface waters like rivers and oceans, sometimes defying expectations, as I've shown in a few of my previous videos. One of the most important places where groundwater shows up in civil engineering is at a dam. That's because groundwater flows from high pressure to low pressure, and a dam, at its simplest, is just a structure that divides those two conditions. And what do you know? I've got an acrylic box in my garage full of sand to show these concepts in real life. You can imagine this soil sits below the base of a dam, and I can adjust the water levels on either side of the structure to simulate how groundwater will flow. Blue dye placed in the sand helps show the direction and speed of water movement below the surface. A higher level on the upstream side creates pressure, driving water in the subsurface below the dam to the opposite end of the model. I'll be the first to say it, this is not the most mind-blowing revelation. You probably could have predicted it without the fancy model. But to a civil engineer, this is not an inconsequential phenomenon, and for a couple of reasons. First, water seeping below a dam can erode soil particles away, a phenomenon called piping. Obviously, you don't want part of your structure's foundation to be stolen from underneath it, and piping can create a positive feedback loop where failure progresses rapidly. I have a whole video on piping that you can check out after this one. The second negative effect of groundwater is less obvious. In fact, until around the 1920s, dam engineers didn't even take it into account, leading to the demise of many early structures in history. The engineering of a dam is largely an exercise in resisting hydrostatic pressure. Water in the reservoir applies an enormous force to the upstream face of a dam, and if not designed properly, that force can cause the dam to slide downstream or overturn. The hydrostatic force is actually pretty simple to approximate. Pressure in a fluid increases with depth, so you get a triangular distributed load. Once you know that load, you can design a structure to resist it. And there are a lot of ways to do that. One of the most common types of dam just uses its own weight for stability. Gravity dams are designed to be heavy enough that hydrostatic forces can't slide them backwards or turn them over. But to the dismay of those early engineers, pressure from the reservoir is not the only destabilizing force on a dam. Take a look at this pipe I've included in the model that shows the water level between the two boundaries. If the base of a structure was below the water level shown here, the groundwater would be applying pressure to the bottom, counteracting its weight. We call this uplift pressure. Remember that the only reason gravity dams stay put is because of their weight. So you can see how having an unanticipated force effectively subtracting some of that weight would be a bad thing. Many concrete gravity dams have failed because this uplift force was neglected by engineers, including the St. Francis Dam in California that killed more than 400 people when it collapsed in 1928. Many consider this to be the worst American civil engineering disaster of the 20th century. Unlike the hydrostatic force of a reservoir, uplift pressure from groundwater is a much more complicated force to characterize. It exists in the interface between the structure and its foundation, in the cracks and pores of the underlying soil, and even within the joints of the concrete structure itself. The flow of groundwater is affected by soil properties, the geometry of the dam, the water levels upstream and downstream, and even the subsurface features. How these factors affect the uplift pressure can be pretty challenging to predict, but engineers do have to predict it. After all, we can't build a dam, measure the actual uplift force, and add weight if necessary. It's got to work the first time. One way to characterize groundwater flow around structures is the flow net. This is a graphical tool used by engineers to estimate the volume and pressure of seepage in the subsurface. In simple terms, you divide the flow area into a curvilinear grid, where one axis represents pressure and the other represents flow. If this looks familiar, you might notice that a flow net is essentially a 2D solution to the Laplace equation, which also applies to other areas of physics, including heat flow and magnetic fields. Developing flow nets is almost an art as much as a science, so it's probably a good thing that groundwater problems problems are mostly solved using software these days, but we can still use flow nets to demonstrate a few of the ways engineers combat this nefarious uplift force on gravity dams. And one common idea is a cutoff wall. If water flowing below a dam causes so many problems, why not just create a vertical wall to cut it off? We do it all the time. But how deep does it need to be? Some dams might have a convenient geological layer into which a cutoff can be terminated, creating an impenetrable envelope to keep seepage out. But many don't. Cutoff walls can still reduce the volume of flow and the pressure, even if seepage can still make its way underneath. Let's take a look at the model to see why. I've added a vertical wall of acrylic below the upstream face of my dam, and we'll see how it affects the flow. The groundwater flow lines adjust to go under the wall and back up to the other side of the model. If you look closely, you'll see a slight decrease in the uplift measurement pipe below the dam. The only thing I changed between this model and the last one was adding the cutoff wall. So why would the pressure decrease on the downstream side?
In the new economy, average people are becoming millionaires faster and easier than...
The flow of groundwater is described with a fairly simple formula known as Darcy's Law. Besides the permeability of the soil, the only other factor controlling the speed water flows is the hydraulic gradient, which consists of the difference in pressure over the length of a flow path. By adding a cutoff wall, I didn't change the difference in pressure between one side of the model and the other, but I did increase the length of the flow path water had to take below the dam, reducing the hydraulic gradient. I can sketch a flow net over the model to make this clearer. The black lines are equipotentials. They connect areas of equal pressure. The blue lines show the directions of flow. Without a cutoff, the flow paths are shorter, and thus the equipotential lines are closer together. With a cutoff wall, the equipotential lines are spread out. That means both the volume of seepage and the uplift pressure at the base of the structure have been reduced. Cutoff walls on dams have a long history of use, and nearly all large gravity dams have at least some kind of cutoff. It can be as simple as excavating a wide area of the dam's foundation before starting on construction. And that's a popular choice because it gives engineers a chance to observe the subsurface conditions and make sure there are no faults or problems before the dam gets built. Another option is to excavate a deep trench and fill it with grout, concrete, or a slurry of impermeable clay. For smaller or temporary structures, sheet piles can be driven into the subsurface to create a cutoff. One final option is to inject high-pressure grout to create an impenetrable curtain below the dam. The other way to deal with seepage and uplift pressure are drains. Drains installed below a dam do two important jobs. First, they filter seepage using sand and gravel so that soil particles can't be piped out from the foundation. Second, they relieve uplift pressure by removing the water. Let's see how this works in my model. Upstream of my uplift monitor, I've added a hole through the back of the model.
Okay, so this is this is basically what our drain tile and our sump basin is doing on our house. Exactly what he's showing here.
To drain seepage out. Instead of flowing all the way downstream, now some of the seepage flows up to and through the drain. And you can see this in the streamlines of dye flowing in the subsurface. Again, the effect is subtle, but the uplift pressure monitor is showing a slight decrease in pressure compared to the original configuration. There's less pressure on the base of the dam than there would be without the drain. Plotting the flow net over the model, you can see why it behaves this way. The drain relieves the uplift on the base by creating an area of low pressure below the dam. You can also note that the drain actually increases the hydraulic gradient by shortening the flow paths, so there's actually more seepage happening than there would be without the drain. However, because the drains are installed with filters to reduce the chance of piping, that additional seepage is often worth the decrease in uplift pressure. Many concrete dams include a row of vertical drains into the foundation, and some even use pumps to depress the groundwater level further, minimizing the uplift. I can simulate this by lowering the downstream level as if a pump was removing the water. Watch how the flow lines adjust when I make this change in the model. Like drains, these relief wells create more seepage below a dam because of the greater difference in pressure between the two sides, but they can significantly reduce the uplift pressure and thus increase a structure's stability.
This mistake is costing Amazon Prime shoppers. Are you still using Prime because of it?
Yes.
I've been using dams as the main example of managing groundwater flow, but lots of other structures have similar issues. Retaining walls and temporary shoring have to contend with groundwater challenges, including caissons, which are watertight chambers sunk into the earth to hold back soil during construction. Remember the worker I mentioned in the intro? He was on a site near a caisson. It's typical to dewater a structure like this, meaning the water is pumped out, creating a dry area for construction crews to work. Let's take a look at how this works in the model. I'm simulating the act of pumping water out of the caisson by draining out of the model at the bottom of the structure. When a caisson is dewatered, it's essentially working like a dam, separating an area of high pressure from low pressure within only a short distance between them. And as you know, distance matters when it comes to groundwater because the shorter the flow path, the greater the hydraulic gradient, and thus the higher the volume and velocity of seepage. If you look closely, you can see the sand boiling up as the seepage exits the soil into the bottom of the caisson. This elevated pressure in the subsurface and high velocity of flow means that the soil particles themselves aren't being strongly held together. All it takes is a little agitation for the soil to liquefy and flow into the bottom of the caisson, creating a sinkhole that can easily swallow anything at the surface. One way of mitigating this hazard is dewatering the soil outside the caisson. Construction crews use well points, small, evenly spaced wells and pumps to draw water out of the soil so it can't seep to areas of lower pressure. Caissons can also be driven deeper into the subsurface, creating a condition similar to a cutoff wall on a dam. They can even go deep enough to reach an impermeable layer, creating a better seal that prevents water from flowing in through the bottom. Thankfully for that worker in BC, his colleagues were able to rescue him before he was consumed by the earth. Next time you see a dam, retaining wall, caisson, or any other subsurface construction, there's a good chance that engineers have had to consider how groundwater will affect the stability. Even though you never know they're there, some combination of drains and cutoffs were probably installed to keep the structure and the people around it safe and sound.
Hello, baby.
Okay, so that was just to give you guys a better visual going back to this here, of like how drain tile and sump basin can affect the groundwater path around our structure. And it's really pretty cool.
Yeah.
So, you know, and typically we're not dealing with enough head pressure on the groundwater with a normal foundation to deal with the loss of soil like he was talking about. But we do put filters because we don't want the fine particles washing into our washed rock and into our drain tile and that. It'd be a minor issue for us if it did with the ground level, but you would have like sinking around the foundation if all of that filled in. The bigger issue with it would be that then our drain tile system would fail. So, okay. All right. So before we move on all the way from water vapor stuff, I want you guys to take a look at your psychometric charts again. And we're going to look at another way that we can use this. So it's helpful for us to understand how ventilation airflow can work for us or against us. So today it says it's 40 degrees outside and 82% humidity. So can you guys find and chart, you know, get your dot placed on your chart for where that area is? 40 degrees, 80%, 82% RH. Okay.
34 degrees.
So if you find there's horizontal lines, if you follow it to the left, you get to the dew point. If you follow it to the right, you get to, it says humidity ratio, grains of moisture per pound of dry air. Okay? So what we're looking at, just to the right of where it says humidity ratio, grains of moisture per pound of dry air, we've got a scale that goes 10, 20, 30, 40, 50, and so on, all the way up to 200. You see that?
Yeah. So it's not like 90.
So how many grains of moisture would the air outside today have?
90.
Nope. So this, we're looking at this scale right here.
Oh, that one.
Oh.
35?
29, 28.
Yeah, I'm gonna say, let's just call it 30. So not the dark numbers,
Oh,
the ones, these here, not this dark one, but this row right here,
oh yeah. Okay.
okay? So we got 30 grains in there. So then, if we were to take and warm that air up to, let's say 70 degrees, so we bring it into the house. So instead of going to the left to find our 100% line, if you follow that line that shows the grains of water, if you follow that right until it intersects with the 70-degree line, from our temperature dot, our 40 degrees, 82% RH, if you follow that line horizontally to the right until it intersects with our 70-degree mark, what is the approximate relative humidity of that air now?
29.
Okay, so we're going from our point here, we're coming across until we intersect with our 70-degree line.
Oh, like 5%?
29%? Maybe.
Wait, what are we
Yeah,
trying
so
to
it's
find?
more than 25, less than 30, 27,
29.
28, something like that, right?
Yeah.
So that's pretty dry air, isn't it? So if we had a water problem in a house and we needed to dry it out, could we open the windows today and dry the house out if it was 70 degrees inside the house?
No.
Yes,
Yeah.
pretty significantly, right? Okay. So let's go, let's say we have a cold winter day, it's 0 degrees out and it's 99% relative humidity outside. Okay? Can you chart that temperature in RH on the chart?
20 degrees?
0 degrees and 99% relative humidity.
Okay.
Okay? Then if we follow that or that grains of water line across to 70 degrees, what is the relative humidity of the air now that we've warmed it up?
Below 10%?
Mm-hmm. Be at like 6 or something.
Mm-hmm.
So if it's really cold outside and we ventilate the house at all, it's going to dry it out significantly, right?
So we need to do more at our house.
So then let's look at the opposite. Let's say that we want to ventilate our house and it's 85 degrees out and it's 90% relative humidity. Mark that one out. What do we get for our, how many grains of water per pound of dry air? 140?
168?
Yeah, like 160 something, 100, yeah.
Oh, 80 degrees you said. Did you say 80 degrees?
Yep. Or no, I said 85, sorry.
And you go all the way up till you hit the,
So you follow the temperature
till you hit
line,
90 degrees.
90% RH,
Yeah.
draw a mark on that, and follow the line to the right, and you find out, so we're at like 166 grains of water. And so then on that line, we can only go over a little bit. You know, when we hit, by the time we hit 81 degrees, we're at the dew point for that air. And so if we're ventilating with that air in a house that's 70 degrees, our ventilation system has to get, how many grains of water in 70 degree air at 100% humidity?
110.
Okay, so we gotta get rid of 56 grains of water to ventilate with that air, or we're gonna have issues with it. So, and like the grains is like a measure of mass, and it's the exact same scale that the grains that are in your bullet, like you have a 160 grain bullet. So, and then 1 pound of dry air is approximately equal to 2 55-gallon drums.
Wow.
So if you take a 160 grain bullet and drop it into 2 55-gallon drums full of air, that's your 80 degrees or 85 degrees, 90% RH.
That's insane.
There's a little stuff. Big,
And then it gets to 100%.
So a thimble full of water and 2 55-gallon drums of air at 85 degrees is 90% RH. So
And how much air?
1 pound of dry air, which is approximately equal to 2 55-gallon drums.
Wow. So quite a bit of water though to be float.
Wow, okay. Now think of you piling up a ton of 55-gallon drums above you. How many pounds that would be? That's just
But then
air. That's
again-
nothing.
But just and then again the air cools as you go up.
So it gets more dense, so it's heavier.
So it gets less water.
Okay, so we'll jump back into this later on when we get into heating stuff. For now, I think I've overwhelmed you guys enough. And okay. Okay. All right. So the main point of that is because a basement is below grade and the soil tends to be around a 45-degree average temperature, humidity gets to be really, really important to manage. And that's what I was hoping to have you guys see with this. Like when we have warm, humid air, which we get a lot of rain typically in this area, and so generally our relative humidities in the summertime are pretty high. And so because we're in a wet climate, or a like moderately wet climate, over 30 inches of rain a year, we have humidity, moisture issues to deal with. And as soon as we take that warm, moist air into a cold basement, we get problems. And so when you're in a basement evaluating and there's water everywhere, just keep that in the back of your mind that you have to be able to know what the conditions are and understanding the dynamics of temperature, and air and moisture can really help you to know, like, okay, are the conditions today such that I would expect to see water on everything in this basement? Or would I expect it to be dry today, and so because it's wet, then we for sure have a leak issue? So a lot of times it's very obvious. Like, there's a hole in the wall and there's water pouring out of it. Like, that's not from condensation.
Let's do the condensation here.
So, but there's other times, like in that story I told you earlier about the people with the exercise mat, like if you put a rubber mat on a floor and it stops the evaporation, could you theoretically have condensation build up between the concrete floor and that mat, even if there wasn't all that water under the floor? You possibly could. So that's where you have to, the more you understand the physical science, the more prepared you'll be to diagnose issues. And a lot of times carpenters misdiagnose issues because they don't understand the physical science. Okay? And so the better grasp that you have on the driving forces of nature, the better prepared you'll be to go into and look at, like, so we have a problem. Here's our algebra for today. We want to solve for this unknown, and we have this known and this known and this known. So based on those, which one is my problem? And by understanding that, it will help you come to the right conclusion. So, where when you don't understand, you may come to the completely wrong conclusion because you took an incorrect input. So, okay, so do you guys have a better understanding of why basements can be cold and damp in the summer and why they can be cold in the winter? Okay. Incidentally, like this here is called stack effect. Okay? It's the same principle that causes a chimney to work. So as air is heated, which even if we have a little temperature difference, the air is going to want to rise and flow out of the chimney. That's what causes and creates the draft on a chimney. Without stack effect, without that warm air being more buoyant than the cold air around it, you would get no draft out of a chimney and they wouldn't work. So chimneys for millennia have relied on the principle, the stack effect principle.
Like your fishing in the wilderness or whatever, you have like a fire, but like you can't close it off.
Mm-hmm.
What would be like the main reason why like you wouldn't have like the chimney wouldn't work?
Well, you have to be able to create heat. And so that's why a lot of times, like, so I don't know the engineering behind like size of firebox to size of flue, like how much draft a certain size flue can create and like how they size that to the stove. I don't know that engineering, but in the old days, like when we had these massive fireplaces with the like hook and you'd swing the big kettle under there, you know, like those big things, they had massive flues, like, you know,
Yeah.
Santa could slide down kind of flues, you know.
Yeah.
And they didn't draft all that great because the space was so good. I mean, so good. The space was so big, so you had to get a big enough fire to create enough heat to start to warm that air in the flue before it would actually start to really rise out of it and create a good draft. So you start with, you know, a small fire and try to get that air starting to warm and start to create a little bit of rising air through it so you get some draft, and then as your fire grows you can make a bigger and bigger and bigger fire.
So that's
And,
why they have those little things where you can adjust the airflow on that side of the chimney.
Yeah, usually, so typically those are used in, like, you get a big fire going so that you don't have just like a jet engine going out sucking all the heat out of the house. Because if you have air rising like crazy out of it, you're not just pulling the smoke from the fire, you're pulling air from the whole house. And so you damper it down, you adjust it so that there's getting enough flow so that the smoke is still exhausting, but it's sucking less air out of the house. So,
The jet engine go through the whole house.
okay. Okay, so if we have humidity, high humidity and like condensation all over our basement in the summertime, what would be the best way to address that issue?
Cold and damp in the summer.
Yeah, if we had condensation all over in the basement in the
Use the air
summertime.
exchange.
Put a dehumidifier in,
Okay,
Or use air
because
exchange.
that way you can
Okay.
rely on it. Never gonna be too heated.
how would the air exchange help in the summertime?
Well, if you had like an air exchange that could bring the hot air from like up above and bring it down, circulate it through, so you can dry.
Okay, yeah, that won't necessarily work. So your furnace system could do that because the furnace will circulate the indoor air. Air exchanger isn't really designed. It's more designed to exchange inside with outside air.
Maybe
So-
insulate it.
Yep, insulating would help tremendously, right? Because then all of a sudden, the hot, humid air can't get to the cold surface, so you solve your condensation that way. Circulating your air through your furnace, like to get better mixing, that would definitely help. You would also want to provide some form of dehumidification, whether that's air conditioning or a big hog dehumidifier or something like that. So, okay? Okay, all right, so waterproofing for below grade walls. So there's two specific legal terms that the building code has. There is damp proofing and waterproofing. So typically, any material to meet the code specified to comply with the building code as a waterproofing material, it has to be at least 60 mils thick. Or maybe it was, well, if it's below 40. So if it's below 40, it's damp proofing. And then damp proofing also doesn't have to comply with a whole set of different codes. And so the black asphalt tar that you see that used to be put on every basement that was ever built around here, that is only a damp proofing material. It's not waterproofing. So one, it doesn't meet the specified thickness. Two, it's not a manufactured tested system.
No
So-
roll. Waterproofing,
What's that?
no roll.
Yeah,
Is it?
Yeah.
How thick is that?
that's 60 mils.
Is it?
Huh. So, but even if we put on a spray applied waterproofing system, you have to use a mil gauge and you have to check the thickness of it when you're installing it to make sure you're getting it. I think it's got to be over 40 mils. But that sheet stuff with the plastic backing on it, that stuff is at 60. So,
Use that stiff flop.
so we've got to be at the code specified thickness. If there's a warranty on the product, it has to be very clearly described. And in your contract, if it's not warranted, you have to very clearly say what is not covered by warranty. So any waterproofing, there's an entire Agriculture, Trade, and Consumer Protection Code regulating waterproofing in Wisconsin, mostly on the marketing side, where you are barred from implying that there's any warranty, and then if there is a warranty, like you have to have it all completely described and clearly written out. And so because of that, it is an extremely high risk type of work, meaning that the ATCP code offers a customer a ton of remedies that can be very detrimental to the contractor. And so,
A lot of
like,
remedies.
a lot of remedies, yeah, like where they can sue for like double damages and sue for this and sue for that. And your recourse, if you don't get paid, is like nothing. So, you can file a lien, that's it. So, anytime that waterproofing work is done, a contract has to be extremely clear and explicit, and the work has to be done very, very well, because if there are any leaks, it's going to be a mess. So, we want to, number one, we want to use, for us, our perspective is we want to use a manufacturer's system that's like clearly detailed, that the manufacturer stands behind, and then we have to follow those manufacturer instructions exactly. So, you know, if they have places where they want a double thickness, you put a double thickness. If it has to be mechanically fastened to the wall, you mechanically fasten it. Like, you do everything according to their system. Because if you end up in a lawsuit and in court it comes out that the way the product was put on did not comply with the manufacturer's instructions, all of a sudden you just get to pay whatever damages, you get to pay the customer's attorney fees, you get to pay all these things. And so it's very, very important that each detail is done exactly according to the manufacturer's specs. So otherwise you get to pay and pay and pay and pay.
So do you guys charge a lot of money then for doing like basement ceiling and stuff?
I don't know if we charge a lot of money. We have what we feel is a pretty rock solid contract. So that basically lists, so this isn't warranted, that isn't warranted, this isn't warranted. Just because it's waterproofing doesn't mean it's actually waterproof, you know, and like all of this stuff. So basically to say, we're going to put this on and we don't know if it's going to work, but we hope it does, and if it doesn't work, it's your problem.
Nice.
So, yeah, sadly that's where it's at. You know, if it does leak, we'll go back and fix it, because we're pretty confident in the system. We've been doing it for years, and with the peel and stick, we have never gone back to fix it. Like, we've never had a leak ever. So, but we're doing that manufacturer's system exactly. Oh,
The problem is nowadays, like, people are so happy. Like, you have to do, even if it sounds stupid, like, you have to put it in the contract. Otherwise, like, they'll just turn around and be like, "Oh, I can sue these guys for $1 million." Like,
Caution.
what? That actually works.
Moisture in some form around every building site, so it's important to deal with it before it infiltrates and becomes a problem. W.R. Meadows is a cost-effective, quick, and easy to apply waterproofing solution. Melroll. Melroll is a flexible, versatile, dependable, roll-type waterproofing membrane made of polymeric waterproofing and high-density polyethylene laminated together. This self-adhering waterproofing membrane is used to waterproof both vertical and horizontal building components. Melroll can be applied to concrete, masonry surfaces, wood, insulated wall systems, and metal. Before applying, make sure that concrete surfaces have cured for at least 72 hours and all substrates are clean, dry, smooth, and free of spalled areas, voids, and sharp protrusions. Apply Melroll in dry, fair weather when the air and surface temperatures are above 40 degrees Fahrenheit or 4 degrees Celsius. Be sure the concrete is near the air and surface temperature and do not apply Melroll to frozen concrete. For applications with air and surface temperatures as low as 20 degrees Fahrenheit, use Melroll Low Temp. Use Melroll XLT for applications in extra low temperatures, down to 0 degrees Fahrenheit. Apply Melprime adhesive to surfaces that will be covered within 1 working day. If left exposed overnight, additional adhesive must be applied. Install detail strip horizontally along the wall where it meets the footing, placing half the material up the wall and the other half onto the flooring. Extend the material 4.5 inches beyond the outside corners. Slit the extended portion of detail strip lengthwise. Place the horizontal flap up onto the footing and bend the vertical flap around the wall. Repeat this procedure in the opposite direction for the other side. Special polymeric membrane strips are on both sides for positive membrane-to-membrane adhesion in overlap areas. For horizontal applications, remove the release paper along the edge, then position the Melroll. Pull off the remaining release paper, running the roll from low to high points so the laps will shed water. Stagger the end laps and overlap all the seams at least 2 1/2 inches. A handy overlap guideline is printed 2.5 inches in from the material edge on each side to assure proper overlap coverage and assist in maintaining a straight application. Apply a double thickness of Melroll over construction, control, and all expansion joints, as well as over cracks greater than 1/16 inch wide. Remove the release paper from Melroll, then apply it vertically in lengths approximately 8 feet long over the top of the horizontal detail strip at the footing. Overlap the seams at least 2.5 inches. Tightly butt the edges of the membrane and apply pointing mastic at the corners. Also apply pointing mastic at least 1/8 of an inch thick and 1 inch wide to the top edges. Once positioned, immediately hand rub the Melroll firmly to the surface, removing any bubbles or wrinkles. Next, pressure roll the entire surface to assure positive adhesion. Before covering, conduct a thorough inspection and make all necessary repairs immediately. Cover tears and inadequate overlaps with Melroll. Slit fish mouths and patch. Seal the edges of all patches with pointing mastic. Where applicable, horizontal applications can be flood tested for 24 hours. All leaks should be marked and repaired when the membrane dries.
Why would you put Melroll on flat?
You need to remove it underneath, like if there was some space under there.
Or for like on flat roofs. Probably.
On a roof.
Yeah.
On a roof?
Yeah, like in the
Flat roof.
Yeah, like a lot of, there's a ton of commercial spaces that usually they'll have like a built-up roof with foam layers, and then they'll have fiberboard layer, and then they'll do hot tar, like a multi-layer hot tar, and then they'll put gravel on it or something like that. There's a lot of different, some pretty crazy flat roof systems out there, but
Wow.
So the one thing that they didn't do in there, like they said seal the top edge with the pointing mastic. Usually we'll go and there's those 1-inch wide aluminum strips, or the aluminum detail strip. We'll put those on, mechanically fasten the top edge, and then you run your bead of pointing mastic on top of that. So it just, that adhesive on that Melroll stuff, if it's exposed to the sunlight, can let go and it'll like flop down. And so that's where like either the pointing mastic or the mechanical fastening. We like the mechanical fastening because it's really, really certain. Excuse me. I've seen projects where people use the Melroll, like they use the primer, they use the Melroll, but then they didn't either put the pointing mastic or the mechanical fastening, and like within a few weeks or whatever, you drive by and it's flops down and peeling off the foundation. The other thing with it, if it's going above grade, it has to be covered because the sunlight will destroy that polyethylene sheet on the surface. So if it gets left exposed to the sun for like more than 6 months, it will completely wreck that surface facing on it. So
then you usually put like aluminum stripping like that.
yeah, like coil stock, or you can put on like, could screw on expanded metal lath and stucco it, or you know, there's all kinds of different options, but if one way or another it has to get protected from the sun. So, or you can end it like right at grade so that the soil will cover it. Some guys will end it like 2 inches below grade. So I like it to come up a little bit above, but generally, and so the reason why it's okay to end that stuff just below the grade surface, actually we'll get into that on the backfill stuff. There's just very little water. When you only have that much water, there's very little pressure and push on that. And so like the stuff we went over on concrete, if the concrete is cured properly, it's going to be pretty water resistant, and so if there isn't a big crack in it and there's no pressure on the water, it's not going to be any issue. So, okay, let's take a 5-minute break. We'll come back at 10 o'clock, and then we'll jump into this backfill. Okay, guys. So what we're going to look at now is on backfill. So ideally, we will have this top one on the well-graded clean gravel or gravel sand mix, or let's see, or the bottom left one, the well-graded clean sand.
What's the difference between well-graded and poor-graded clean sand?
Well-graded is relatively uniform in size. Poorly graded is like a pit run with clean sand that would have everything from like sand up to like cobblestones in it. So, so what you see, what we're looking at on this chart, you have a description of the backfill material, and then the right column, so both this and here, this is your design lateral soil load in pounds per square foot per foot of depth. So if we had, you know, let's say we have an 8-foot deep basement, and we're going to backfill this thing with clean sand, so it's 30 pounds a square foot per foot of depth, so it's 8 feet of backfill times 30, so it's going to be 240 pounds per lineal foot of wall. It's going to be that much in force pushing inward on that wall.
Really?
And so we just have to make sure then, if you're in the design stage, you have to make sure that you can design a basement wall that can retain that. Or if you have a design and you put the basement in and you're like, so I've got this really crappy backfill, you know, or this one here, and I want to see if I can just use a drainage material. Like, have you guys, any of you guys seen that Meldrain product?
Yeah.
I'll find it. Okay, we're gonna look it up quick before we go on. Let's go.
I may have, but I don't know the name.
Okay. Oh, you got a better picture than that. Here we go for sure. Okay, so the Meldrain, it's this product with this like dimply surface, and it's got this geotextile over the face of it. Let's see if we can get a better picture of it. Okay, here we go. So you see this here? So it's got this dimply surface with a geotextile over the face of it. This dimply surface is like 3/8 of an inch thick. So like we would use it like in an application like this. You put the plastic backing against the wall, the dimples create a 3/8 inch airspace, and then it has the geotextile over the face of it, so that water in the soil hits that, drops right out, and we would usually wrap it over our footing on down to our
So is that
drain tile.
Is that so you can just use like normal soil?
Right,
Backfill?
because then you could use the native soil to backfill.
Is it
So-
worth it, or would you rather just call and say?
Well, that's where sometimes it is worth it, but then that's where we have to look at this stuff and say, you know, if we've got this really nasty soil, native soil, can I use that for backfill if I'm doubling the lateral load against my basement wall?
Oh,
And so, you know, that's when you look at this and you make a call to the building designer and you're like, hey, if I backfill this thing with clay and it doubles the lateral load against the wall, is that going to be okay? And in most cases, they'll be like, I don't know, let me talk to an engineer. So, yeah,
Hi. Is it fine if Jack borrows that Ryobi Scarfer, brings it back like Sunday or something?
sure.
Okay.
See ya.
Thanks.
Yep. Let's see, so it's important for us to realize that these like silty clay soils generate a significantly higher force against our wall than sand does. So the other part is design lateral soil loads are given for moist conditions for specific soils at their optimum densities. Actual field conditions shall govern. Submerged or saturated soil pressures shall include the weight of the buoyant soil plus the hydrostatic loads. So if we look at this, I have wall number 1 here, and my footing, and I backfill this thing with well-graded, clean sand, and let's say we're 6 feet deep. Is well-graded, clean sand going to hold any water? No. So any water in here is going to go straight to the drain tile and drain away. Okay? Wall number 2. So I get a total lateral load of 6 times 30, which is 100. What's that?
180.
180. Okay, it's 180 pounds per lineal foot. Okay. Wall number 2, I decide I'm going to use this mel drain on it. Okay. And then I'm going to backfill with clay. So I'm going to have a lateral load of 60 pounds per foot of depth. So 60 times 6 is what?
360.
360. But then when I look at the code here, it says submerged or saturated soil pressure shall include the weight of the buoyant soil plus the hydrostatic loads. So, what is water weight per cubic foot? You should know this, Neil, from diving stuff.
That way something.
It's like, oh, I think like around 16.
Yep, it's like 62.5 pounds per cubic foot. So, you know, whatever I have here, you know, let's just say it's a column of water. If it's completely saturated soil, which with clay, we could actually get it completely saturated. So my worst case load would be another 60, basically equally in the soil load. So I get another 360. So I could have 720 pounds pushing on this wall versus 180 if I backfill with sand. Wow. So do I want to backfill with clay? Probably not. Okay?
If you have a really, really, really thick wall, you could.
What if you had to like
Otherwise,
already backfill in the middle?
2 foot wall. Did
2 feet?
2 foot with a floor between it?
Dingle
Brace
where
it?
we filled like 2 or 3 feet up with sand.
Okay.
We used the mel drain and the rest we used.
Okay. Okay.
Stuff the rest of it.
Yeah. Okay.
The top of it.
But that site too wasn't, that one wasn't like organic silts. That was more like a, clay gravel, poorly graded gravel and clay mix.
Yeah.
So at a 45 instead of one of these at a 60. So, and then you put the 3 feet of sand underneath, 2 or 3 feet. So, yeah. So, and that's understanding some of this stuff will help you in the field, because are you going to have a perfect solution you get to do every time? Maybe, but sometimes you may not. And so that's when having this for a background, it'll let you have enough knowledge to be like, okay, well, I know that the absolute best is to backfill this thing with clean, well-graded sand. But I don't have that option today. So what's my second best thing that I can do? And so, okay.
62 pounds per cubic foot of water?
Yeah, it's like 62.48.
Oh, yeah.
That's the number one most important principle for shipbuilding, right? Like, how much water does it displace? Because then you know how much weight you can have. You know, like, I was listening to this one book on naval stuff, and they're like, talked about a ship that displaced 70,000 tons.
Of water? 70,000 tons?
Yeah, I mean, that's what that was its displacement. It's like, woo! So, okay, so this next slide here, I pulled a bunch of these slides out of, this is straight out of the Wisconsin Building Code. And so this here is a table for plain masonry foundation walls. So when they say masonry, that would mean like a concrete block, okay? And so you'll notice in here, it says solid on some of these. So it's got note B, you go down to note B, solid grouted hollow units, okay? So with no reinforcement, no rebar at all in this wall, and not grouted, if I have a 7'8" wall, I can put 4 feet of backfill with an 8-inch wall and a 30-pound soil. So like if we go back here, this is where my soil load numbers matter, right? Okay, so 8-inch block, 7.5 foot or almost 8 foot tall wall, I can only backfill at 4 feet or less with this type of soil, with that type, and with this type. So the same on all of those. If I want to go to 5 feet of backfill, I can do it with an 8-inch block and that type of soil, but then in this one I have to go to a 10-inch block for the next two. If I'm going to have 6 feet of backfill, I got to go to a 10-inch block for that one and a 12 for this one, and I got to go to a 10-inch core filled for that. That's what this chart is telling me. Or if I have an 8-foot wall and I want to backfill at 8 feet, even in this type of soil I have to have a 10-inch block that's core filled. This one I have to have a 12-inch block that's core filled. And this one, an analysis in compliance with ACI 530 or reinforcement according. So
What is a 12-inch block? What's the difference?
the width. Okay, and so this is really helpful. All of a sudden, if you're out in the field and you're like, oh nuts, is this wall going to be able to support if I have to change my backfill? Now you can go and you don't have to call an engineer. You don't even have to call a building designer. You can look at this chart and be like, oh, yeah, shucks, this will work if I grout it. Okay? The next one's here. Now these are for reinforced. We got 8, 10, or 12-inch reinforced block walls. And this here, where D is greater than 5 inches. So if you read on the notes, I'm not going to make you read the notes, but so if we have our concrete block here, okay, they have 2 cores. If this is the backfill side of the wall, when they say D 5 inches or greater, that means the distance from the backfill side to our reinforcing bar is 5 inches or greater. Okay, that's going to be hard to achieve in an 8-inch block and actually get concrete to go around that rebar, because like the edge of this block is like 1.25 inches, 1.5 inches. So that bar is going to have to be almost touching the one side of that core. So, but the interesting thing with that is, you know, then if we look at this one, this is what you can do if your bar is 6 3/4 inches away from the load side. And this one here is when your bar is 8 3/4 away. So, and then what they do in here, so let's say we've got a 9-foot block wall and we want 8 feet of backfill on it, and we've got this 45-pound soil. We need to have number 6 bar 64 inches on center. So that's vertical. So every 5'4", we have a vertical number 6 bar. And the numbers are how many eighths of an inch. So that'd be 6/8,
Yeah.
which would be 3/4. So, okay. And that's in a 12-inch block.
Wow.
So that's where this stuff, the really cool thing with the building code is they have, like, if you can take the time to look in it, it has an answer for almost every engineering question you would have for a residential structure. So, You know, and so then we could look at, you know, here's for 10 and 12 inch. So, you know, we can see here, we want to backfill 8 feet. So the same, they're dropping us down to a 10 inch, and our spacing from the fill side to the bar is smaller. And so, you know, on the other wall we had number 6 at 64 inches. Here they dropped to 48.
It's only going on 9 feet, huh?
So typical wall is going to be, you know, here with probably around 6 feet of backfill. And so, you know, with this soil type, we only need a vertical every 56 inches, and then we get into this one and they got to be at 48. Technically, if we have the possibility of like completely saturating that soil, we'd have to double that or cut the spacing in half. So that's the cool thing with this soil, is all of those are very free draining soils, and so because they just can't be saturated, if we have a functioning drain tile system at the bottom, we don't have to plan for the extra water in that. So, okay. Any questions on that before we leave?
Where did you say all this information was?
Code.
Okay, so I have it bookmarked here, but so you can go to this dsps.wi.gov, which is the State of Wisconsin Department of Safety and Professional Services. So I have this one here, the 1 and 2 family dwelling, bookmarked. So they have a bunch of stuff on here, like different rules, forms, questions, and then in this menu here they have administrative rules and statutes. So you click on that and you get to Uniform Dwelling Code, Commercial Building Code, Old Buildings, Plumbing. So for us, for residential, we're governed by the Uniform Dwelling Code. So we go there, and then if I want to look at construction standards, I go there. If I want energy conservation there, heating, HVAC there, electrical, plumbing, and so on. This stuff here is in Appendix C, which gives you like span length tables for different woods. Gives you some details on deck stuff. I think it has, no, this is the one I was looking for. So this here gives you, this appendix gives you a bunch of stuff. Okay, this one has the span tables. This is interesting. It gives you all your engineering numbers for. Excuse me. You get all the engineering numbers for different species of wood. So like here for like eastern hemlock, you get your FB and your modulus of elasticity, which are the two numbers that you need to calculate the load capacity of any member. So that's really handy. So the details on handrails, stuff for erosion control, like how to draw erosion control plan, things on dewatering. What do they got here? under soils, how to classify soils. I think this is the one that had all the backfill information.
If you hit Control F, you can search it.
Yeah, I don't know what it would exactly search for, but I guess I could go back and look at the tables.
Just any of the keywords.
I thought it was Control G. Control find.
Control F. Yeah. F for find.
So here's some stuff on, some things on like shallow footings, you know, look up how much insulation you have to put, and then like what areas. So, let's see. So they've got all of that stuff. This one here is on decks. So, then like construction standards, oh yeah, here's where it went. So the nice thing is they have all these like indexes on actual statutes. And then we go foundations. There we go, soil lateral load, and then you have this PDF table on that. So, and then here's the stuff on the foundation walls, wood walls, floors, all that. So everything that you need as far as like standards, engineering stuff to figure out structures, and like if you let's see. So we'll go over this. One of our classes, probably more than one, will go into this to help you guys get a good understanding of it. Let's see, wall design. So like if you want to figure out what size header you have to have, so you can go in here, walls, wall openings, headers, then you hear header size. The size of headers shall be determined in accordance with the spans, blah, blah, blah. Go to this table, okay? So we go to this point. Here we go. So this is what you can look at here. So if you want to know what you can do with framing, so if you have a 2x3 stud, you can go. No, it won't work. So we can go 2x4, maximum laterally unsupported stud height. So the maximum height of the stud without lateral support, or blocking 10 feet. You can space them 24 inches on center in either of these applications, like single story, the top story, or you can go to 16 inches on center and they'll work for the first level on a 2-story, but it won't work for the bottom level on a 3-story. Or if you're putting a center basement wall holding up the floor, you can space the studs 24 inches on center. So 2x5, which would be like your 2x6, you can space those 24 inches on center. So anyway, so you can see that, and then you get down into here. Allowable spans for headers supporting a roof ceiling assembly. If you have a 24-foot wide house, you're in zone loading or roof snow load zone 1, and you have two 2x4s together, they can span 2.5 feet. If you want, if you've got a 5-foot opening, you need 2 2x8s, so on. So, you can make it real easy, or you can do structural analysis on it, and so on. So,
Back to those lateral loads, is that the same for all like basement walls, crawl space walls, that kind of stuff? Does it change if you use an ICF? Or is it
so
still the same?
ICF, anything that's poured concrete is gonna be stronger. So, substantially stronger. So,
This is just if you're using block.
this is for block. So, it can give a good baseline, you know, like, if you've got a poured wall, like, let's say you've got a, you know, we have a 8-inch poured wall that's 8 feet tall, and we know we're gonna have 7 feet of backfill on it, you know, we could probably get away with number 4s at 48 inches on center, just because the poured concrete is stronger. And so the one question that I have on the building code that I haven't gotten a good answer on is like, the building code only gives you credit for the verticals. But the horizontal bars are gonna strengthen it too. So I don't know, like, I need to find an engineer that's willing to like give me some time to answer questions, but like why you get no credit for the horizontals. Because they should be doing something, but for the building code, from the building code perspective, all they really want, like they really want the verticals. So for us, you know, ideally we're gonna have them have a L bent on the bottom of them and have them cast into the footing and going up, because then it ties our footing and our wall together too. So, but looking at this tables, I always put the verticals in the middle of the wall. But it's only doing a little bit there, like the farther toward the inside we get it, the more strength it's going to give, but we need enough cover over it. So you need like, I don't know the exact depth for like the engineering to get full strength developed on it, but like I'd say 1.5 inches in from the face of the concrete. You know, so when we're going and we're tying rods in, if we tie it so that we're 1.5 inches in from the inside face of the form, that's going to give us the most strength. So, because if you remember from that video we watched on the concrete beams, you know, the bar gives us the tensile strength, and so the farther away that is from the opposite side of the beam, the load side of the beam, the more strength it's going to give us. So, okay. Any questions else on that?
Can you build a whole house out of insulated concrete forms?
Yes. Yes.
The Shooties do it all the time. Right now they're doing, I think, they're doing like a set of 5 or 6 of them right now. All
Okay.
over
So I have one video here that I thought was really good. I think it's about 11 minutes. So I actually have two. That one just to show you guys like a really, really well done. It was cool. So let's see if I
When did you get out?
JCB, huh? So I don't know that I agree with them putting that poly down over the soil like that. Oh, I guess they are. So that's fine like that. The poly should be in contact with the concrete. That's a different one where they put it poly down and then put the rock on top. So you notice on this that they got all their verticals sticking out of the basement floor. Like, so basically they're pouring their floor and their footing in one shot. When they're squaring out, they're pulling corner to corner, and they're laying out for their wall. So it's a precast concrete wall with foam insulation, and then a concrete face and a concrete face. And they're bracing them in place.
That's pretty strong.
So then he was putting a gasket to go in between the panels.
Those windows in the dirt?
Yeah.
Oh, wow.
That's a lot of steel.
I should say, holy cow. Holy cow.
So now they're filling that space in the wall and doing that floor. So he's vibrating that wall. I guess you guys can see the point like that. So there they're just like puddling the concrete a little bit.
He was using the wrong trowel though. He was using the steel instead of the magnesium.
Okay.
What in the world?
Well, that place looks expensive.
They're building a prison.
So then they're sealing all the outside joints. Putting on some kind of primer system. And then spray on waterproofing.
Yeah, it looks like Neil, but really fat.
That's what I was saying.
It's like me.
No, he doesn't have the liner above his, covering his forehead, and the liner below his.
Then more insulation. And a drainage sheet.
I don't know what.
Drainage like that mill drain stuff. And they're backfilling with P-rock.
Wow.
So that was quite a system.
That was like the perfect system.
That was awesome. This one here, this one they're doing is an insane amount of work. Like you look at these guys.
Yeah, that was. Just smooth it all
Like
out.
on clean sand.
I think it's like washed rock probably.
What are they, like from India or something?
So they're scraping it out.
All by hand.
Learn to walk on it. It's hard pack.
Is that insulated?
Yeah, it's all expanded polystyrene to create this form.
That came off.
Then they're putting like some type of waterproofing seal on it or something. Yeah, rolling out sheets there, like something like a melt rail, kind of melt roll. Then some other product.
It's not even gonna be a basement by the time you get done.
Yeah, really, you know.
I mean, I guess this is only just one day so far.
This is a lot of days.
He's got to be like a month in.
Like, look at these, how much structure that rebar, like, they're doing a double grid.
Is that more risk of fracking or no? Like the crack?
Oh, that concrete's gonna be like 8 inches thick with a double rebar grid in it, like.
They're building their house on block.
They expect half of it, I think, lift up 2 feet.
You know, and look at, they got all this work that's tied into the floor.
It looks like some super high slope.
Where is this, Canada?
I don't know.
Yeah, so we're setting all these ICFs. Now we're gonna skip through this a little bit.
It's Legos for adults.
There they got ICFs almost up.
Oh, that's a lot.
And they're setting this span stuff for its main floor. Looks like pour the main floor and walls at the same time.
It's like human 3D printed.
Legos for adults.
That looks like plastic.
It's gonna be like $1 million house.
So then you're continuing with ICF.
And they're still on the first level.
Time.
Yeah.
So that's where like we need to understand like what the customer's budget is, and like then we need to also understand what it costs to do things. And if somebody comes and is like, yeah, I want this house and this is my budget, be like, something, either the budget needs to go here or the house needs to go there. Like, so, okay. So then this one here, I wanted to show you guys because like this guy has a video of like a very realistic, real world problem. And so my question for you guys is like, do you think he took the right way to solve the issue? And if you were the general contractor or the concrete guy in this job, would you have done it the way he did, or would you look at some other way?
Today, last time we were here, we caught up with Mike and just started the excavation. We're dealing with water. We ran into a lot more than just a little bit of water. We had confirmed really whether or not it was due to defrosting and just the overall groundwater level. Mike, come on man, don't be shy. So last time we were here, we were talking, we were down in this area here, and I think you had noted that you had hit ledge, but we were also dealing with water, and water being a big issue in the hole.
Yep.
So I think it was that day you had reached out to a geotech engineer who wanted to make sure that we were doing our due diligence and efforts to, whatever we're going to build here, we want to make sure we know how to best position it.
Yeah.
What was their recommendation?
All right, so they came out, we dug a little test pit for them. They got to, observe the soil conditions and like the bearing capacity was great. The issue was we had a lot of water. So in order to stabilize, make sure that we provide a solid footing for this house, their recommendation was to install 6 inches of stone underneath where the footing's gonna be and then compact it, just to make sure that everything does stabilize.
And not only, so the stone is to help kind of give us that base layer like you said.
Yep.
But also we dealt with ledge, right?
Yeah.
So we have ledge right here, which last time we were talking about the shale, which now it looks like shale because it's been hammered up. We're actually raising the elevation of the house. What and how much are we raising it?
We're doing about 6 inches.
And why is that?
that's to give us some separation from where the water table is. So the fact that we hit bedrock, right? Your water kind of like percolates down through the different layers of soil, and then when you hit the bedrock, it's sitting there, right? It can't go through. We're bringing in the 6 inches of stone to help lift this up, give the water somewhere to go underneath that footing, so then this house isn't just sitting in a puddle the entire time.
So if that concrete footing was on that bedrock, it would just always be wet, right?
Yep.
So now we're creating a little separation. Now, it's important to note this house is actually already risen up.
Yes.
And one thing that we're really conscious about is what that front stoop might look like in comparison to the street.
Yep.
So how much are we bringing this house up?
So we're bringing up, it's going to be pretty close to level with the side.
Which will look really nice.
Yes. Yeah, it's not going to be lifted up with this giant mountain. So you don't have to
It's
worry
not
about
going to be on
that.
this pedestal
Yeah.
like some of the
No.
homes that we've seen.
But in comparison of what the elevation was before
It was
to
really
where it is
nestled
now,
down.
yeah, we're down in a hole. As you can see, we got a beautiful duck pond out back, that low area.
Not really a
So,
duck pond.
no, we're gonna have to address that, and so we'll start taking care of that now.
So let's walk this way. But while we're walking, we're gonna jump over this here. So over here, are we in the location of the 2-car garage? Close?
The 1-car garage, right here.
1-car garage is here.
Yeah.
So okay, I got you. So we actually have a little bit more of excavation to do.
Yeah, we do.
Yeah.
Yeah.
So we're actually standing 1-car garage, and this is actually your mud road.
Mud road.
Right. And that
And it
works
goes
out.
back, and the reason it bumps out back there is where that staircase goes down to the basement level.
Gotcha.
And then your 2-bay garage, as you pull in, is back over where that puddle is right now. So we gotta start addressing that.
So it's interesting to stand over here because looking back at the excavation, you're probably about 7 feet, and
Yeah.
here you're probably closer to 3.
Yeah.
So it kind of goes to show how much we have to really bring up a lot of this land and how critical it's going to be to work with not only the site guys but the civil and the overall, the overall team to make sure that we're grading this in a way that doesn't look like it's mounded.
Yeah.
And that's the biggest concern. One of the things that came up is that, in communicating with the client, we explained the benefit of raising this house up for the longevity because of water. But one of the questions came up was, well, is it going to be too hot? And that's something that, again, going back, the house was nestled in. We don't want to put this on a pedestal. We want to really be thoughtful in it. But it just goes to show, like, we have these low points in the lot, and we're at bottom of elevation here, and we're actually starting to see, this is our base layer, the 6 inches of stone that they're recommending.
Yep.
So from here, what is our next step?
So we got about another day of bringing stone in. Then we're gonna compact that, get it nice and stable, make sure everything binds up. Our civil engineer will come back, and they're gonna pin all the corners for our footing.
In the 6 inches of stone?
Yep, yep. And so then our foundation guy can come in, we're gonna start putting, get the footing prepped and ready to go. And then while they're doing that down on the main house, that's where we can work on these smaller areas with the garages where we're only gonna have frost walls.
Right.
So we only have to dig down, this we only have to go down 3 feet, so over there, we're gonna be barely scratching the surface.
Right. Right, and then the two locations of the garage are both slab on grade,
Yep.
with the exception of the back corner of the garage has a staircase to get down to basement level as our second means of egress there. Cool. So as far as pumping this water out, is this something that we're doing on a daily, or is this pump going to run continuously until we're out of hole?
It's kind of day to day right now, depending on what we have for weather, warm temperatures, things thawing.
What are we finding when we're getting here in the morning?
We get roughly 4 inches of water in the bottom of the hole. So you run the pump for about an hour. It does a pretty good job of drying it up, and you can kind of see. It's mucky right now because they've been playing around in it, but usually it's not as bad as that.
Yeah, I think Bob was saying it's actually pretty clear water, so it's pretty evident that it is groundwater.
Yep.
Say this pump goes off, we come back tomorrow and the stone is wet. Is there any concern with geo for that stone to be wet after it's compacted, or because realistically this is the condition this stone is going to live in for the.
That's why we're going to run around the compactor, and as you do that, you're going to find a few areas that the ground will chew up some of that stone. But if you keep hammering it in, it'll bind up, and then that's what they want to see is when it gets solid.
Yeah, really good compaction.
Yep.
So beyond that, once we get our footings in place, you know, one of the details that we're always including is our capillary grade. And it's even more important here, being that we are dealing with groundwater. If that footing is wet, we don't want water wicking up through that footing, through into the foundation wall. So we'll have that, you know, basically waterproofing layer on top of our footing prior to our walls going on, and then we'll have our waterproofing layer on the outside of the foundation wall, which will create a monolithic seal between footing and wall. Beyond the capillary action, we also want to make sure that we're preventing water from ever entering into the basement. So there'll be things like the vapor barrier that will be underneath the slab, which will be monolithic, that will prevent the slab from getting wet, with sump pumps. A couple weeks ago, I had posted something on my Instagram. Hey, what sump pump does everyone recommend? What sump pump did we end up going with here, and why?
Was it Zoller? I think it's the company, right?
Zoller, yeah.
Zoller, yeah. So there, between talking, like you reached out, and I think it was.
I think I was a Zoller 75 or something like that.
I forget the
It was
model
small,
number.
right?
Yeah, so I ended up buying it. It's a whole kit. It comes with their basin that you can tie right into. It's actually a gasketed lid on that, so that's something we're going to use for our passive radon as well. Go right out of that some bit. And so they have this really nice kit that we just ended up purchasing 2 of them for this house.
And how big? Do you remember how big they are?
It's about a 10-gallon basin.
10-gallon basin.
Yeah.
So we'll have one on either end of the foundation.
Yep.
And something you skipped over there real quick, the gasketed lid tying in our passive radon allows, since we're going to have that perimeter drain on the inside, we're also going to have the secondary perimeter drain on the outside.
Yeah.
So it's really these redundant systems, but rather than tying in our passive to that drain, we can actually tie that passive right into the lid of that
it's
something.
a vented lid. Yep.
Cool. So we'll touch base when we get a little bit further along on this job. Hopefully coming out of the ground with some concrete. I have a deal with Mike that once he goes vertical, he gets an office trailer here. Until then, stay tuned. We'll see you guys next week.
What do you think? Think it'll work?
I don't think it would work.
A lot of water.
It's a lot of water.
That's the real
Red
world.
rock, though.
Might help to run that ventilation system we talked about earlier.
Mhm. Yeah, so when they said passive, what's the difference between passive and active?
Well, active is what continuously happening.
Okay, so the main difference is they'd be the exact same. Passive one just won't have a fan in it. So then just whatever ventilation wants to happen out of that vent pipe, it can vent out if it wants to. With the active, you throw a fan in it, so it has no choice.
So like on a place like that, if you're building it up, 2x4, 2x6 construction, and you do like a passive vent or even an active one, and you put that 4-inch pipe in the slab, run it to the gravel, and you run it up through the attic, and you run it through a wall cavity.
Yeah.
To hide it.
Yeah, you can run it anywhere you want. So the only thing that they want on them, anything where you have a possibility of radon, you have to have the fan outside of the conditioned space so that all the pipe inside the conditioned space is negative. So that in case you have a joint that didn't get sealed or something, you're not blowing that pressurized out of the joint back into the house. So that's why they put either the fan outside on the outside of the house, out of the rim joist, or the ideal is to have it come out through the roof, and then you stick the fan up in the attic outside of the conditioned space, and then it just punches through the roof like another plumbing vent. So, but
Do you think it would help to run a sump pump, or not a sump pump, what is that stuff called? Drain tile right through the middle of their house?
I don't know that it would make any difference, because that washed rock that they're putting in, water can just freely flow through that. So it'd just be totally unnecessary, that the tile around the perimeter and then that washed rock. Like the whole entire thing is going to connect. Like the water level at one end of that site is going to be the exact same as at the other.
So when you're building on a hill is when you want to have it on both sides? And if you don't have washed rock underneath?
Well, the house site is going to be level, right? So
Right, and so
they're,
if you didn't want to have the drain tile on inside and out.
oh, it doesn't matter, whether it's level or on a hill, you want inside and out. We have to, because it's building code.
Oh,
So, so in their thing, they're putting 2 pits just because, or 2 basins, just because they know they have a major water issue.
Yeah.
And then that way they have a little redundancy. If one pump fails, then the other will keep enough water out and give them some time to where they can get another one, get the other replaced and so on. So,
Man, I wonder where that is, where they're right at Pepper. It's like,
we ran into a job like that, you know, that one up we did for Russell Welch. That foundation was sitting right on the sandstone.
oh,
So parts of it, we had to step the foundation because we couldn't dig any more deeper because we were rock smack onto the sandstone. Wow. So they scratched it away as much as they could, but
is sandstone considered bedrock up here?
yes.
So when you're putting your drain tile down, do you put the drain tile, do you have anything under the drain tile that you would add, or is it just on this?
Right on the dirt, right next to your footing, just like that. So. Mhm.
doesn't matter whether this is really
Right,
put on clay, put in
yeah.
just like the teens. Right on.
I thought we put gravel under it. Oh no, we put sand under it.
No, we put, first we put yeah, we did put sand. Put sand under it, just because.
At where?
The deans,
Oh, okay.
we put sand under it.
To like
just
flatten it out, level it
Yeah.
out and stuff.
Yeah.
Yeah, and that's totally fine, we just want the tile to be like below the top of the footing. So, oh, the one thing they talked about in there was putting a capillary break over the footing because the footing's sitting in water. Really good practice. So we could like put a sheet of plastic, just like 6 mil poly over this. We could use like a peel and stick like the Melroll or roof underlayment, or we could put like a spray-on sealer. There's any number of things that we could do on this.
Put that on before you pour the wall?
Yeah, before you pour the wall. So because he talked about capillary action, so because of the pores in concrete are like this ideal size, you know, we talked the other day about curing concrete and how much is like trapped within the pores of the concrete. So if this is like sitting in water here, there's our nice waves. Because of the size of the pores in here, water can just flow.
Up through the,
And they say, like, it can wick all the way up into here enough to where you could, like, theoretically rot out your sill plate at the top of that wall. You know, or if you're finishing this basement, that moisture can come in here, because it's gonna wanna go somewhere. Water flows from more to less, right? So that's where putting that capillary break there will keep that from wicking up into the wall. And then they put their waterproofing here, and then they pour their floor. So if you're in a site where you know you have wet soil conditions like that, it becomes really, really important. Like all of a sudden, like all the red flags start waving of like,
yeah,
we got to be really careful, and maybe we need to go take some extra measures. So, which in their case, they did. They put down 6 inches of washed rock, and really good move, because that washed rock for them, you know, now all of a sudden their footing is up here, and they have, you know, 6 inches of washed rock here. And then they're going to dig their sump basin in here. So if their pump is here, then like theoretically this water should only get there, which should mean that the bottom of their footings should be dry. And like, then, you know, they put their drain tiles up here, and then their floor is up here, and so the washed rock creates this basically airspace between the soil and the house. So really, really good move. Like it does so much for our house that it should almost be done on every single house no matter what. It's just adds a couple $1,000.
Yeah.
And most people are like, I don't want to spend $2,000 on that. Like it's only going to be there for 200 years. You know?
Yeah. Build it good.
Well, you know, spending $100 now saves $1,000 later.
The problem is that it snowballs. You know, you do that every step through the project, and the house that you originally were looking at spending $250 on is now $600.
Like that one project that was taking forever, like that high work one.
Which one?
First video.
Oh, right. Yeah, I mean, that was an insane, like, totally bomb-proof. Like, they'll never have a problem with that house, right? But it only cost $150,000 to build that basement. Right? So that's what you gotta be able to weigh. Like, that's the job of a general contractor, is every step along the way is you have to be able to, like, evaluate your cost benefit, do that analysis continually of, like, here's the cost, here's the benefit it provides for this customer. Does that benefit outweigh the cost enough to do it?
So the best is if you can find this naturally.
So one, for example, an architect designed the place for the customers. I don't know if they pulled something off the shelf or if they did their own design on it. We insulated it, and it was up by Bayfield on Lake Superior. And we showed up, and they have this huge kitchen, probably about the size of this room, you know, and then this living room. So it's like this size of the room, and this corner here, they took and they put this big, huge screened porch on, and that's the whole view of the lake. So from the kitchen and the living room, you look out and you see screen porch and screens. And if you want to see the lake, then you got to go out there, and like, it was like, I told the builder, I was like, what in the world? He's like, I know. He's like, it's been insane. And he's like, the best part, he's like, first overview on the plan. He was like, wow, this is a huge attic space. Are you sure you don't want to put like a loft into this attic space? And they're like, oh, there's not enough room. And he's like, okay. So he builds the place. They come up there and they're like, look at all that room in the attic. We need to use that. And he's like, I told you that. And so then they put these windows in, did all this stuff, and they had designed this really steep garage roof. And so the big window out of that loft looked out over this 6-foot long breezeway and then a 12 pitch garage roof. And the builder said, the best thing was, he said, the architect came out to look at stuff, and he walked upstairs and he looked out the window and he was like, wow, I didn't realize that I was going to look right out at the garage roof. That's kind of sucky.
Oh my god!
And he was like,
wow.
So,
wow.
Yeah.
Well, some people, it's just like the things don't click with them.